joint work with Bo Wagner. So in this talk, I'd like to share some of the recent thinkings that Bo and I have about whether we can formally define a notion called informational substitutes and complements. So we're very familiar with substitutes and complements of goods, but when it comes to pieces of information, do I have a similar notion that we can make use of, and how such a definition, like if we can come up with a reasonable definition for informational substitutes and complements, can help us understand the strategic play of players in games. So what I'm going to do is that I'm going to formally introduce the Bayesian view of information, and the prediction problem, and also the prediction market problem. So that's what motivates us to start to think about that we need a notion of substitutes and complements for pieces of information. And then I'll talk about some of our attempts in defining substitutes and complements of signals. So this is largely conceptual because I'm going to introducing our definition. Okay. And also, I will be discuss just one prior definition on this topic that we're aware of and why we don't think that helps us in this particular purpose. Okay. And after that, so certainly the substitutes and complements of signals is not just for the prediction problem. So we want it to be general for all decision problems, but actually it turns out to be the case that prediction problems are basically complete for the purpose of thinking about complements and substitutes of information. And we'll apply our definition to thinking about the equilibrium of prediction market. So the game theoretic equilibrium of prediction market. I'm not going to talk about the specific technical derivation about how we get the equilibrium result, but I just want to summarize the result so far that we have with that respect. And I'll conclude with a few future directions. Okay. So let me start talking about information. So when we talk about information in decision science or economics, we often take the Bayesian perspective of information. So the typical model that we think about is that, oh, there is some events of interest that a decision maker may care about, and that is the random variable E. And for example, the event of interest that I'm using as an example could be the outcome of a replication for a behavioral experiment. Okay? And then information is represented as signals. So there are, again, random variables. So individuals may have different signals, A, B, and C. So they're all like random variables. And for example, a particular signal could be represented as the outcome of some related events to the behavioral experiments that we care about. Okay? And since we're talking about the Bayesian view, and there is a prior distribution, so which is a joint distribution of the possible outcome of the event of interest and the possible realizations of all the signals. So this is the common Bayesian framework that we're thinking about private information. Okay? And unlike the physical goods, so people have utility or value for just having the physical good. So for pieces of information, it doesn't seem to be sufficient for us to just say that, oh, I have a thirsty of information. I just want to own information. Just owning a piece of information giving me utility. So in some sense, just to talk about information is not enough. We need to think about information in conjunction with the decision-making process. So here we're introducing a decision problem. And decision problem is defined by a set of possible decisions that a decision maker can pick from. So that's the set D. So for example, a particular decision for this example could be, I'm going to follow the recommendation of the original result. So assuming that the original behavioral experiments makes a recommendation about what I should be doing, I'm going to follow that recommendation. So that's my decision. And an alternative decision could be that I'm going to ignore that recommendation and do whatever I want. Okay? And a decision problem typically is associated with the decision maker's utility. And here the utility function is a function of the decision that the decision maker makes and the realization, the actual outcome of the event of interest. Okay? So with the decision problem in mind, we now can talk about what's the value of information. So the value of information, just to follow the prior work, basically can be defined as the expected value of the utility that the decision maker can get if acquiring that information and also follow the best decision given the realization of that information. So essentially, if I'm thinking about a signal A, which is a random variable, I'm taking expectation across all possible realizations of that random variable, and I'm thinking about the decision maker's maximization problem that is conditional on a realization of the signal A, and because condition on this, the decision maker should have a distribution about the outcome of the event of the interest E. And then the decision maker wants to make a decision to maximize the expected utility here. Okay? So this is the value of information that I'm referring to. Okay? So far so good. So that's information and decision problem. And a special case of a decision problem really is just a very simple prediction problem. So in a prediction problem, the action space or the decision space now becomes the report space, which is just the probability simplex over the possible outcomes of the event E. Okay? So really, we're just asking the decision maker to report a distribution about the event E. And one particular way to reward the decision maker or thinking about the utility function of the decision maker is to use a proper scoring rule. And a proper scoring rule is a scoring function that takes the report of the decision maker and the actual realized outcome of the event E and return a real value. Okay? For example, a widely used proper scoring rule is the log scoring rule. So it's just to reward the individual according to the log of the probability reported for the outcome that actually happened. Okay? And I want to emphasize proper here. So proper here really just means that it's incentive compatible. So a risk neutral participant would want to truthfully report the belief that he has after getting the information. Okay? So for the decision problem, the value of information can be simplified because we have the proper scoring rule. So in some sense, a decision maker, after having the signal realization of A, will have a conditional distribution for the outcome of the event, and that's representing as PA. So PA is a distribution of E conditional on the realization of the signal, like big A turns out to be the lowercase a. Okay? And because we're using a proper scoring rule, it means that the best action or the best decision that the decision maker can have is to truthfully report this distribution. Okay? So the value of information is reduces to this form. And if we think about the inner expectation here, so this is the expectation. So this is essentially a function that only depends on PA. Okay? So I'm going to call this function JPA. So this is basically the expected score function if someone is truthfully revealing his belief. Okay? And I'll come back to this later, but in the scoring rule literature, there is a very close relationship between this function J and the corresponding proper scoring rule. So there's essentially almost a one-to-one mapping, and this function J is always a convex function. Okay? That comes handy to us. So that's a special case of a decision problem. It's a prediction problem. And if we're using a proper scoring rule, we can essentially ensure that a risk-neutral participants will truthfully report their belief to us. So we get their information. Okay. So that's one agent case. But we'd also like to move from a one agent case to a multiple agent case. So thinking about that multiple agents all have information to contribute, and how can we get that information? And that becomes a prediction market. So I'm talking about a very specific form of a prediction market, that's Hansen's market scoring rule. So essentially, this is a shared version of a proper scoring rule. So we're still considering the event, whether a study is going to be replicated or not. But think about that, we start from some initial probability distribution over the two possible outcomes, and the participants can just come and sequentially change that probability distribution to whatever they think is correct. Okay? So we have different participants that are going to report different probability distribution. Okay? And the market uses the proper scoring rule. And if we look at a participant at time t and reported RT as the probability distribution, that participant is going to get the scoring rule difference between his report and the previous report. So essentially what it does is that instead of directly rewarding the participants using a scoring rule, it rewards the improvement that the participants make using the scoring rule. So we're only rewarding participant T based on how much he improves beyond the previous prediction. Okay? So in some sense, anyone can come to this market and changes the current market prediction. So the current report measures the population's collective belief to a certain degree. And I just want to mention that, so I call this a market, but this is essentially a sequential changing of changing of the probability reports. But it is indeed a market in the sense of in practice, this type of mechanism is often implemented as a market maker mechanism. Trading contracts looks like this. So this is essentially a futures contract. It pays off $1 if the starter is replicated and $0 otherwise. Okay. And prediction market has many applications and has been shown that they make good predictions compared with alternative method. I just want to mention some of the recent results that we had coming from actually using prediction market to predict the reproducibility of some of the psychology studies. So psychology as a field, they're aware of that many of the experiments may not be reproducible. So, and over the past few years, more than 200 researchers in psychology, they collaborate on what's called a reproducibility psychology project to reproduce a set of selected studies from the top 3 psychology journals. So far, about 100 has been tested. So the replication of about 100 studies has been completed. So we basically piggybacked with this reproducibility study, and we set up prediction market for 41 psychology studies before the replication actually happened. So that's what we did, and we basically like psychology researchers to participate in this market and use the market to say whether the market price successfully predict the outcome of the replication. And it turns out that the price correctly predict about 71% of the replications. So compare with the surveys that we conducted before they participate in the market. So just the simple average of the survey would correctly predict about 58% of the replication outcomes. And if we use their self-reported confidence to weight their report, that only gets about 50% of the replication results correct. So self-reported confidence doesn't seem to be very reliable.
Is the prediction market more accurate about non-replicatable or about replicatable studies?
Yeah, so it's both. So you might be curious about out of the 41 psychology studies, how many are actually replicated? So it's a little disappointing. So it's 39% were successfully replicated, but and a larger set of the studies. So basically, we only set up a prediction market for 41 studies, but so far about 100 has completed, and even in that set, it's about around 40% that were successfully replicated.
Just by saying no all the time.
So, well, if yeah.
So Kevin's question was, I guess, if I interpret correctly, were people biased saying something will be replicated when it's actually not?
We didn't notice the bias between these two. Oh, okay. So from our data, we didn't notice that.
Prediction markets generate a price, right? What does it mean that they create?
Right, exactly. So if we interpret the price as the probabilities, so what the price suggests is that the market should correctly predict about 96% of the star days. So if you really interpret the price as the probabilities.
I don't know what you mean by the market predicts. Does that mean that it's a number bigger than 0.5?
Yeah, so 71% is like, if I'm taking that the price is higher than 0.5 as just predicting that direction, that's 75%. And if it takes the price to be 60%, like if the price like Anne says, 60%, we know that with 60% of chances, by doing that, that's going to give us the correct prediction. And if we interpret that as like the market price as a probabilistic prediction, then roughly what the market suggests is that we should be able to use the market to predict about 69% of the outcome of the replication.
I don't want to take it on a tangent, but it seems that it's also in the strictness of the definition of replicability, how well does it have to replicate?
Yeah, exactly. So basically, we define that like because first it's a direction, and second is like with the right like p-value. So essentially like strong enough, and that's also consistent with what the reproducibility project is using as was considered as replicated. Okay, so I hope that like this means that there's some potential interesting applications for prediction markets, and it seems to be at least working to a certain degree. But what's puzzling to us is that it just seems to be working, but we don't really understand very well about how information is being reviewed in the market and being aggregated in the market. So especially when considering that the participants are strategic. So when using a market scoring rule, because the market scoring rule uses a proper scoring rule, if a participant only participate once, we know that it's the best interest for the participants to truthfully review his belief. But since it's a market, a participant can participate more than once and can come back later on. So there's this strategic concern about how are they going to decide when and how much to review their information. Okay? And there's some work about this, trying to understand the game theoretic equilibrium of a prediction market. So I just want to mention that, so early on in the previous session, so we had a discussion about that game theory is not very useful for understanding the behavior of financial market. And here a prediction market is essentially a futures market. So arguably, it's slightly easier than a stock market because it's a futures market. The outcome will eventually be revealed at the end. And second, because of the mechanism that we're using, so it's essentially a one-sided mechanism. Everyone is trading with the mechanism. And hopefully that makes starting the prediction market a relatively easy thing for understanding the strategic behavior. Okay? So the typical model for starting this problem is just to model the market as a Bayesian game. So essentially, we have all the same information structures, so common prior, signals, and event of interest. And in addition to that, and the typical assumption is that there is a fixed order of participation. So arguably, this is a very strong assumption. But so far, like, it's unclear how we can relax this assumption and still gain tractability. Okay? And the model typically either assumes a finite number of rounds or infinite number of rounds. Okay. So what we know so far with that model? So there are some very interesting progress has been made with respect to the information aggregation in prediction market. In particular, Michael Ostrovsky essentially characterize a condition called separability condition. So it's a condition about the securities payoff and the underlying information structure. And if that condition is satisfied, he shows that essentially all information is fully aggregated in the limit. By saying in the limit, it means that as time approaches to infinity. So if we're considering the perfect Bayesian equilibrium for any market scoring rule mechanism, so in the limit, information is fully aggregated. So that's pretty nice. That's a very strong result, essentially saying that at least at the end, information is fully aggregated if there is a perfect Bayesian equilibrium. Okay. And a follow-up work by Chris Eyre and collaborators essentially extends the setting to consider risk-averse participants. So without specific emphasizing, like in my talk, all the work like uses risk-neutral participants, and this is probably the only work that considers risk-averse participants. So this set of results sounds good. At least it gives us some hope that information is eventually aggregated in a prediction market, or can be aggregated in a prediction market. But it doesn't say much about when the information is aggregated. So the limit can be very long. And if the information is not revealed early enough, a market is not necessarily very helpful. So there's some work that we have been doing trying to understand the structure of the equilibrium. So one of the early work that we show is that for the logarithmic market scoring rule, so a very specific market scoring rule using the logarithmic proper scoring rule, and if the signals of all the participants are conditionally independent, so meaning that conditional on the true outcome of the event, the signals of the participants are independent, then the only equilibrium in a prediction market using LMSR is the O-rush equilibrium. So what does the O-rush equilibrium mean? So roughly speaking, so I'm not very precise here, but roughly speaking, it means that everyone will try to truthfully reveal their information at the first round of the participation. Essentially, if there is an order of participation, then at their first round of participation, they will try to reveal all their information and truthfully. So arguably, this is the really nice equilibrium that we would like to say if we're interested in thinking about using prediction markets to elicit and aggregate information. So I would call this the good equilibrium. Okay? And so Dimitri and Sami shows that, actually, when the signals are independent, so this is unconditionally independent, then in the same mechanism, we cannot have the O-rush equilibrium. So the nice equilibrium cannot be possibly achieved. Okay? And with Alice and Jiezhang, so just a couple of years ago, we showed that with independent signals and in the same logarithmic market scoring rule mechanism, actually the only type of equilibrium is that every participants would try to delay the revealing of their information. So that's what we call the O-delay equilibrium. Essentially, they want to wait until the last round of participation.
Can you provide some intuition for what this independent signal means? I mean, I can understand what's conditional.
Conditional independent, yeah. So that's a very good question. So conditional independent is probably the one that we say a lot. And independent signals, I actually don't have a very good examples. The top examples that I have is that supposing that both of us each observe the outcome of a coin flip, whether it's head or tail, and the event that we're predicting is whether both coins come up with heads. So clearly our information is related to that outcome, but unconditional on that outcome, we have independent information. Okay. A somewhat more realistic example would be thinking about voting. If we think that we vote independently and we're trying to predict whether a candidate is going to get the majority vote, that can be roughly modeled as independent signals. But I wouldn't strongly argue for that. Yeah. Okay. So basically, these are all we know about the structure of the equilibrium in prediction market. And we actually, at this point, have pretty good intuitions about why this happens. So why with conditional independent signals we have the O-rush equilibrium, and why with independent signals we have the O-delay equilibrium. And I'm sure that the intuition makes sense to you too. So in some sense, with conditional independent signals, the signals of the participants roughly can be considered as substitutes, meaning that if your signal and my signal are substitutes, then I want to reveal my signal and profit from that first, because after I reveal my signal, your signal is not going to be that valuable. Okay? And for the independent signals, we have the intuition that, actually their signals are complements, meaning that, I want to wait for you to reveal your signal first, because combining your signal with mine, I have a higher value. Okay? So that's the intuitions. But we struggled a lot about trying to formalize that. So we really couldn't find a mathematical formulation for us to be able to formally say that, in this case, the signals are substitutes, and in this case, the signals are complements. So that really motivates us to just to think about substitutes and complements for pieces of information in general. So for the physical goods, so substitutes and complements are well defined. So for example, coffee and tea are substitutes, and coffee and cake are probably complements. And the definition of substitutes and complements actually are very useful. So there's a strong connection between substitutes and existence of equilibrium in markets for goods and also in the matching markets. So essentially, for the physical goods, it seems to be that the definition of substitutes and complements is crucial for a lot of understanding of the market behavior. So we ask ourselves, can we define informational substitutes and complements that have similar impact? So at least to help us understand the equilibrium in prediction market, but hopefully more broadly applicable to other domains in general. Okay. So that's a long motivation. Now let me start to talk about how we can define substitutes and complements for signals. Okay. So the only prior definition we're aware of was by Börgers et al. So they define, so they had the first formal definition of substitutes and complements of signals. And I just want to remind you that the value of information is essentially the expected value of the expected value of the decision maker's utility when taking the best action conditional on the realized signal. So Börgers et al.'s definition is a direct analogy of the substitutes and complements for physical goods. So essentially what it says is that two signals A and B are substitutes if for every decision problem, so the sum of the value of signal A and value of signal B is greater than or equal to the value of having both A and B. So this notation means the join of the signals A and B essentially means that we have both signal A and B, and plus the value of having no signal, so not seeing any of the signal A and B. Okay. So this is a direct analogy of the complements and substitutes of goods. Okay. So this sounds very appealing because it does capture some of the signals and what we would consider as substitutes and complements. So for example, if the events that we're considering and the two signals, the three random variables are the same, so clearly we're in a situation that signals are substitutes. So any decision problems that involves this event E1 is going to have signals A1 and B1 to be substitutes. Okay. Alternatively, if we think about a different example, if the event here is the XO relationship between the two signals, and clearly we're in the case these two signals are complements. Okay. But we also find this definition to be very difficult to work with. So in the sense of, it doesn't depend on the decision problem. So I highlighted here, this is a definition for every decision problem. So it requires that two signals A and B has to satisfy this inequality for every possible decision problem that you can imagine. Okay? And sometimes signals can be substitutes for one decision problem and complements for another decision problem. For example, if you think about two pieces of signals, one is the price for a tech stock A, the other is the price for a tech stock B, and if my decision problem is whether I want to invest in a tech stock fund or index fund, then these two signals probably are substitutes. But if my decision is which one of these two stocks I want to invest in, these two signals are probably complements. So I need to know both of them. So in some sense, we really want the definition to depend on the decision problem so that we can say something specific just for that decision problem, rather than just concluding that, oh, it doesn't satisfy this definition and we don't know whether it's substitutes or complements. Okay. And the second potential problem that we encounter with this definition is that this definition doesn't depend on the internal structure of the signals. If you think about that, I'm just combining these two events into a joint event E here. and I'm combining these two signals into a joint signal A here, and similarly joint signal B here. So if we're thinking about like E, A, and B, so some of its components are substitutes, but the other part of their components are complements. And the definition of this doesn't consider the internal structure of the signals, won't capture anything represented here. Okay. So we start by allowing the definition of substitutes and complements to depend on the decision problem and also depends on the internal structure of signals. And in order for us to make a definition like that, we need to place a structure on the signals. So the structure that we're considering is the Blackwell partial ordering. So this is a Blackwell informativeness criterion. What it basically says is that the signal A prime is less informative than the signal A if A prime is a gobbling of A. So gobbling of A can be thought as like adding noise to A, or there exists a stochastic mapping from A to A prime. And just like any randomized strategy given A is a gobbling of A. So essentially we're enforcing a partial ordering of informativeness of signals. And we're going to make use of this to define substitutes of signals. Okay? So here is our definition. So the pairwise substitutes. So I'm only going to talk about the substitutes because the complements case is just a change in the direction of the inequality. So we're saying that signals A and B are substitutes. So here we're specifically defining that for a decision problem and for a prior P. So essentially for information structure. And so there are substitutes if for all the signals that's less informative than A, we have this inequality satisfied. Okay? And let me try to explain what this inequality means. This inequality essentially is saying that, the left-hand side is the marginal value of having signal B, in addition to already having signal A prime. And the right-hand side is the marginal value of having signal B, in addition to already having the signal A. So the inequality says that, if A prime is less informative than A, then A and B are substitutes if the marginal value of B given A prime is greater than the marginal value of B given A. Or in other words, knowing more about A reduces the value of B. So essentially it captures the decreasing marginal value of signals. Okay? And the same must hold, like something analogously must hold for like B prime that's less informative than B. Okay? And complements basically just reverse the direction of the inequality here. Okay? So that's our definition. So we're defining that for a particular decision problem, and we're taking into consideration of the internal structure of the signal.
So this looks like a stronger definition potentially, and there might be some A and B that are neither substitutes nor complements.
It definitely can be. Okay. So I don't know whether this is stronger than the previous one because this is like decision problem specific, and the previous one must satisfy for all decision problem. So in general, I still think that the previous one is probably likely to be stronger than this one, because this one, we can define things specific to the decision problem.
Isn't the first one just quantify? Is this condition just quantified over all decision problems?
No. So this is actually for a particular decision problem. So because we have the utility function here.
Right, but isn't the first one just this same condition has to hold for every decision problem? So
not necessarily. So it has to hold for every decision problem, but it has a difference is that it only considers the extreme case of A and B. So here we have the condition of saying that it has to be for all A prime that's less informative than A. Essentially what it's saying here is that, if A and B are substitutes, then any part of A and B has to also be substitutes.
I see. So it's the difference between subadditivity and submodularity.
Yeah, exactly. It does have a connection with submodularity over set functions. Okay. And how much time do I have?
8 minutes.
8 minutes. Okay, great. Okay. So this easily generates to substitutes of a set of signals, because if we want to consider any game that has more than 2 players, we need to be able to talk about substitutes for a set of signals. And what it says is that a set of signals, a set of n signals substitutes, if we're considering, like, assuming any pair of an and aj belong to this set, and revealing any combination of other signals c, and consider the combined signal of an and c and the combined signal of aj and c, they're still pairwise substitutes. So what it's saying is that, so suppose that I've already learned some of the other signals. Now I'm adding my own signal to what I've already learned, and I'm adding your signal to what that's already learned, and these 2 new signals are still substitutes. Okay, so that's our definition. So hopefully it sounds sensible to you. I don't have time to really justify that, but I just want to make, I will make a few comments later on about it. So what's interesting is that our definition is for any decision problem. But we kind of have a revelation principle type of result, basically saying that prediction problems are complete for the purpose of thinking about informational substitutes and complements. So essentially what it says is that for any decision problem U, so there actually exists a proper scoring rule S, such that for all the priors P and all possible signals, the value of the signal in your original decision problem is the value of the signal in my new decision problem with the scoring rule. Okay? And this is actually very easy to prove, basically saying that, assuming that given my signal, I have a distribution R for the event E, and then this D star is my optimal decision with that distribution. And I just set this to be my scoring rule. And it's easy to prove that this is a proper scoring rule. Okay. So what it says is that, so it's without loss of generality to just focusing on prediction problem, if we're considering the informational substitutes and complements. And by focusing on just prediction problem with scoring rules, the value of any signal, as I've shown before, is the expected value of a G function of a prediction, essentially. And this G function is a convex function. Okay? And I think I'm going to skip this figure, but what I want to say that, so there's a very tight connection between convex function and proper scoring rules. And by reducing all the problems, all the decision problems to prediction problem, it'll allow us to make use of our understanding of the convexity of the expected score function. And we actually have other definitions that's equivalent to what I have shown you about substitutes and complements of information. And that give us a level of proof things.
So I missed the connection between the revelation principle and the structure of signals.
The structure of the signal.
So, like, was this enabled by
So,
the substitutes and complements of signals?
no, so this is basically saying that for any decision problem, I have a corresponding prediction problem that's going to preserve the same substitutes and complements property for all the signals.
Right.
So I'm not.
This is a generic statement, though, right?
This is a generic statement. So this is a generic statement, basically for any set of signal, any information structure you're considering. So if you give me a decision problem, I can find a corresponding prediction problem and just started that prediction problem. Okay. So I think I have maybe 5 minutes. Let me just quickly tell you, like, with this definition of substitutes and complements of information, what we can say about like game theoretic equilibrium of prediction markets. So basically what it says is that if signals are strict substitutes, then every Bayesian-Nash equilibrium is the O-Rash equilibrium. So we're considering extensive form game. So the right solution concept probably is something like perfect Bayesian equilibrium. But we're stating this for Bayesian-Nash equilibrium because a perfect Bayesian equilibrium is a refinement of the Bayesian-Nash equilibrium. So this statement is actually stronger. Okay. And this is, in some sense, also tight. meaning that like if signals are not substitutes, then there exists a trading order where some participants would want to initially withhold information. So they won't actually reveal their information immediately. And similar results holds for complements. So if signals are strict complements, then every Bayesian equilibrium is the O delay equilibrium. Everyone try to wait until their last round of participation to participate in the game. And this is also tied in the sense of like if signals are not complements, then there exists a trading order where some participant initially reveal some information. Okay. So what does it mean? So we're also interested in understanding the signal classes. So we know that from the early result, for the logarithmic market scoring rule, when signals are conditional independent, we have the O-rush equilibrium. And when the signals are independent, we have the O-delay equilibrium. And the result I just showed you are for any market scoring rules, so not specific ones. So essentially, just using the definition of substitutes and complements. So the signal classes, we actually can characterize that. So the independent signals are complements in any decision problem where J is associated with the corresponding scoring rule, has a jointly convex Bregman divergence. So J is a convex function, so it has a Bregman divergence well defined. If this Bregman divergence is jointly convex in both arguments, then for independent signals, so they're complements. Okay? So this includes the logarithmic scoring rules and quadratic scoring rules. So the quadratic scoring rule part wasn't known before. Okay? And for conditional independent signals, we're hoping that maybe it also works for other scoring rules. But it turns out that they're substitutes for log scoring rules, but they're not necessarily substitutes even for quadratic scoring rules. Okay? So it's still widely open question about like how can we characterize the signal classes here.
Monotone likelihood ratio property.
Monotone likelihood ratio?
Conditionally independent with the monotone likelihood ratio property.
Okay, we'll check about that. Thank you. I just want to make a few other comments. So substitutes and complements of signals connect to, as you probably expected, submodular and supermodular set functions. So over lattices of signals, but the lattice needs to be carefully defined. Okay. So this also allows us to have some algorithmic results for some combinatorial signal selection problem, because we can leverage results from the submodular set function. Okay. And our definition also have a nice information theoretic interpretation that I didn't have time to talk about. I just want to mention a few ongoing and future directions. So what makes us very excited about this definition is now when we think about the good and bad equilibrium in prediction market, we really want to achieve the good equilibrium. So it opens us the question of, if we know the signal structure of the participants, can we design a scoring function such that with that scoring function, the set of signals becomes substitutes? And that way, we essentially can make sure that the good equilibrium happens. So we're fairly confident that this can be done, okay? Although I don't have all the details yet. And the other open questions are the characterizing signal classes together with the decision problems. So trying to understand when are signals substitutes for what classes of the decision problems and when are they complements. And we're also wondering whether there's any connection more than just the similarity, like at the definition level, between substitutes and complements of goods and substitutes and complements of signals. So thanks a lot.
One quick question, and then we'll kind of prepare.
Could you provide some intuition why conditionally independent signals can be substitutes? Because my intuition would be that they would always be complementing each other.
And what is that intuition?
Given something, I have an independent signal and you have some, and potentially my signal doesn't tell anything about your signal. So knowing your signal should always help me be more certain about the current status.
So it's conditioned on the true state of the world conditional on the outcome of the event. So our information is independent. In some sense, if I'm knowing your information, it gives me more information about the underlying outcome of the event. So I think that's, I don't know whether that's precise, but that's kind of the intuition of like essentially knowing your information give me a little more information about the underlying true state of the world, and things we're making prediction about that, and that piece of information are kind of the common information, the mutual information.
Okay, let's take the rest.
Yeah.